exam questions. Again, if you've got questions, you can put them in the side chat as well, just as we're going along. So let's jump right into it. So got the periodic table here because we're going to constantly keep referring back to this as well. You'll be given this in the exam as well. So table 1 shows the name and relative charge of the particles of a potassium atom, and it just says complete table 1. So it's talking about the relative charge. The 3 subatomic particles are proton, neutron, and electron. You need to know the relative charge of them, but I'm also going to put the relative mass here as well, because that's something else that you do need to know as well. So the relative mass of each of these as well. So filling in the relative charge, the proton is +1. You can remember that it's positive by the P. The neutron is neutral, so that's why it's 0, and it starts with neutron, neutral, so like neutron. And then the electron is negative, so it goes around the outside. The relative mass of each of them, so we say for proton and neutrons, relative mass is 1. And the electron, we don't say 0 because nothing can have 0 mass, but you could say that it's really small. You could say 0.00005, you could say 1/2000, or so on. So it's just a really small mass in comparison to both the proton and the neutron. Okay, moving on. The electronic structure of potassium atom is 2881. The way they've worked that out, in case they don't give you it, is if you go to the periodic table, potassium in group 1 has 19 electrons in it. So we just take the proton number as the number of electrons. So it's got 19 electrons. 2 seconds. 2 seconds. Okay, so as I was saying, the bottom number, the proton number, is the electron number. So potassium's got 19 electrons. So the 19 electrons, the 19 electrons always follows the 288 rule. Anything after that is also 888 for GCSE anyway. So you just keep filling the shells 8 after this as well if you do get more shells given to you. But it's usually the first 3 shells that they test you on. So as you can see with the 19 electrons, 2 plus 8 is 10, 10 plus 8 is 18, and then 18 plus 1 is 19. So that's where 2881s come from. They've drawn the electronic structure of the potassium ion as well. So 2 in the first, and then the next shell's got 8, the next shell's got 8. 1, 2, 3. Oh, potassium ion. Okay, I didn't see that. So because it's a potassium ion, it's essentially lost 1 electron. So if it was a potassium atom, it would have had another shell, and then it would have had 1 electron from there. But because it's an ion, it's lost that 1 electron. So remember, metals, they lose electrons because it's easier to lose 1 electron than it is to gain 7. And non-metals, they gain electrons. Also, make sure you know the charges as well, what the charges change into as well. So I'll just put this here. The charges of metals, they lose electrons and they become positive ions. So in this case, the potassium becomes a positive ion. And non-metals, they become negative ions when they gain electrons. And depending on the charge of that ion, so like 1 plus, 2 plus, 1 minus, 2 minus, depends on how many electrons they've lost or gained. Okay, so for this question here, it says, what's the charge in the potassium ion? Well, we know it's lost 1 electron. We know it's a metal, so it's becoming a positive ion, so therefore it's +1. Okay, potassium has 2 isotopes. Now remember, isotopes, you need to know the definition of this. Isotopes are atoms of the same element where the number of protons is the same, but the number of neutrons is different. So they can ask you that in the exam as well. Give the definition of an isotope. So atoms of the same element, number of protons are the same, and the number of neutrons are different. Okay, so table 2 shows percentage abundance. The percentage abundance is how much of that is in abundance in the air. So for example, the potassium, not in the air, in the world. So potassium 39, this one here, is 93% abundance, and then the other potassium 41 is 7% abundance. So, and these percentages should always add up to 100%. So that's all of them really. You could have more than 2 as well. So it's saying, how is the relative atomic mass of potassium calculated? To work out the relative atomic mass, we get the mass number, the 39 and the 41, and we times that by percentage abundance. So I'm going to work out here to show you how you work out the relative atomic mass. You're going to do the mass number 39 times the percentage abundance for that one, which is 93. You then plus that to the same with the bottom one, which is 41 times the 7%, and then you divide it by both percentages added together. So 93 and 7 is 100. So that one is this one here. Yeah, that's the right one. Okay, water treatment is needed to make most sources of water suitable for drinking. So remember, water that's suitable for drinking, we call that potable water, if it's suitable for drinking. And we get ours from reservoirs and stuff as well. So water treatment includes the process of chlorination, filtration, and sedimentation. Place these processes in the order that they take place during the water treatment. So at first, it's sedimentation, where it passes through the rocks, they're getting the solids out, the big sieve that they're essentially filtering out the solids, branches, and so on. After that, it's the filtration. And then after that is chlorination, where they add chemicals to essentially kill potential pathogens in that water. Okay, some tap water contain chloride ions, which I guess has come from the chlorination step, right? Explain in terms of electrons how a chlorine atom forms a chloride ion. Well, a chlorine atom has the electronic structure. If you look here, it's in group 7. It's got it's got 7 outer electrons because it's in group 7. Remember, the group number is the number of electrons on the outside. So if it's got 7 electrons on the outside, to become an ion, it needs to gain 1 electron. So it's going to gain electrons, which is where you get your first mark from, and then gain electrons because chlorine atom has 7 outer electrons. And then you get your second mark by saying how much electrons is it going to gain. So it's going to gain 1 electron. So gains 1 electron. Even if you just wrote as one sentence gains 1 electron, you would have got 2 marks, but it's better just to be that extra safe that you've got 2 points just to show the examiner that, okay, you know it needs to gain electrons, and the amount of electrons it's going to gain is gaining 1. Okay, why is chlorine added to the water treatment? Again, it's to kill bacteria in water, as we've already discussed. Yep, so killing bacteria that's in the water. So you added chemicals to kill them. We would not increase the pH of the water to 11. We don't want it alkaline. We want water to be neutral. There's too generic to clean water, so it can't be done, not to dissolve insoluble substances. Stay away tap water is not suitable for chemical analysis. Now, whenever we're carrying out chemical analysis, we always use distilled water, and distilled water is essentially purified water. There's nothing in that water except H2O, so potentially you could boil the water and then let it cool down, and that's distilled water. So the reason why we can't just use tap water is because there's still ions present within that water. So other ions, or you could even say impurities, still in the water. So the water is not pure, the water is impure. That's the reason why we can't use it for chemical analysis. So we use distilled water or pure water for chemical analysis. Okay, moving on. A student was asked to distill a sample of tap water. Figure 4 shows the apparatus the student used. So we can see he's got tap water here. He's put a delivery tube in, which looks wrong. The delivery tube shouldn't be sat inside the water there, because when you're distilling, the heat's going to hit the water and the water needs to travel up as a gas, but the tube's been put inside the water, so that's wrong. Then the delivery tube comes on top, so the gas is raising through here, and then it should evaporate down, so that's what the iced water contains. So it says the student made an error when setting up the apparatus in figure 4. This error meant pure water could not be collected in the test tube. Explain what the student needs to change so that the pure water can be collected in the test tube. So just what we discussed. You need to remove that delivery tube from the water line, essentially. So remove delivery tube. out of the water. So bringing it slightly above, so explain that as well. So the gas can move through. So gas can rise when water is heated to go up the delivery tube. To go up. Yeah. Because that's the whole point we're adding heat to it, right? We want to just evaporate up the water particles. Okay, moving on. State what the student should use to heat the water. Well, if you've got a conical flask there, you just want to heat that water, you could just use a Bunsen burner. Okay, question 3. Figure 5 shows some information about a chlorine atom. Again, if they don't give you that, you just have to get it from the periodic table. So we can see it's got a mass number of 35, an atomic number of 17. State the number of protons, neutrons, and electrons in this atom. The proton number and electron number is just that bottom number. So 17 for the protons, 17 for the electrons. To work out the neutrons, you're just doing 35 minus 17. Just working out here. So the mass number, take away the proton number, and that gives you 18. Another thing as well, they might ask you, why do you have to minus the top number, the bottom number from the top number to get the number of neutrons? And the reason why is because this mass number on top, it only accounts for the number of protons and the number of neutrons. The number of electrons are not in that total mass number. And the reason why is because the electrons barely weigh anything. So we've already said it here. The electrons are really small, so we don't count it in the overall mass number. So that's the reason why we can just minus them from each other just to work out the number of neutrons. Another thing they could also say as well is why in atoms from the periodic table, the proton number and the electron number is the same. And it's because all atoms on the periodic table are neutral. There's no charges to any of them. They're not ions. So therefore, if protons are positive and electrons are negative, you have to have the same amount of each in order for the overall atom to be neutral. So for example, with the one that we were looking at, chlorine's got 17 protons, so that's like a plus 17 charge. So I need to get rid of that 17 plus charge to make it overall neutral. And that's the reason why the electrons are the same. Electrons are negative. That's minus 17, so they cancel out with each other, and it just ends up as 0. So when you start changing that electron number is when ions essentially then become present. So yeah, that's why in case you get like a 1 or 2 marker saying why is this the case. Okay, so chlorine reacts with silicon to form silicon chloride. A sample of silicon chloride contains 1.4 grams of silicon atoms and 7.1 grams of chlorine atoms. Calculate the empirical formula for this sample of silicon chloride. Empirical just basically means simplest. If you ask for molecular formula, that's actual amount of molecules that's in it. Empirical is just the simplest amount. So think about if you had a ratio, you're getting that ratio down to the simplest amount. Okay, so we've got the relative atomic masses as well. So we'll do both of them separately. We've got the silicon and we've got the chlorine. So what you do is you get the mass of what there is. So we know there's 1.4 grams of silicon, and you divide that by the AR, so the relative atomic mass of silicon, which is 28. We do the same thing for chlorine. So chlorine, we've got 7.1. Let me just highlight these. And we're dividing that by the relative atomic mass of chlorine, which is 35.5. So if I put that in the calculator, I get 1.4 divided by 28, which gives me 0.05, and then 7.1 divided by 35.5, which gives me 0.2. Now, I can't have decimal numbers in my empirical formulas. For example, I can't write SI 0.05 and CL 0.2. They have to be whole numbers. So you need to get these ratios to whole numbers. So what you can do is you could just divide by the smallest number on each side. So if I do 0.05, I'm going to divide by 0.05 because both of them by 0.05. That's a smaller number. 0.5 divided by 0.05 5, you just get 1. When you divide both the same numbers together, you just get 1. Okay, so we've got silicon, which is 1. Do the same for chlorine now. We're dividing both of them by that. So 0.2 divided by 0.05. If you put that in the calculator, 0.2 divided by 0.05, we get 4. So that means my empirical formula is Si1Cl4, but you don't really need to put that 1 there, so I can just write SiCl4. That's my empirical formula. Okay, so that's how you work out empirical formula, which is simplest ratio, essentially. Okay, the modern periodic table is organized into groups and periods. So remember, groups is the columns and periods are the rows, as we just saw above. State which group and period silicon is found in and use the periodic table. So let's go back up to the top. Okay, so silicon is here. It's in group 4, and the period number is in. So this is period 1. Hold on. So this is period 1, period 2, period 3, period 4, 5, and so on. So silicon's in period 3. So that means it's got 3 shells. That's the number of shells it's got. And it's in group 4, so it's got 4 outer electrons. So that's silicon, group 4, period 3. Group 4, period 3. Describe 2 differences between Mendeleev's periodic table and the modern periodic table. So Mendeleev, what he did was, the biggest thing he did was he left gaps. So at the time of Mendeleev, a lot of the elements hadn't been discovered yet. But rather than him just putting whatever they had discovered just all together, he left gaps, assuming that they will soon be discovered and then fill in them gaps. So he left gaps. He had basically an incomplete periodic table. So incomplete periodic table. Okay, so that's one difference between Mendeleev's periodic table. Another thing was, as we just said, so he didn't have as many elements as there are today in the modern periodic table. So you could just say there was also less elements. In Mendeleev's. Okay, a few other things you could have said as well. Elements ordered by atomic mass. There was no group 0 in his, so there was fewer groups. There was no atomic numbers in his at that point as well. And some of the elements were also different back then as well compared to now. 2 seconds. Okay, next question. So which diagram represents the structure of diamond? So diamond is an allotrope of carbon. So allotrope of carbon. Now what allotropes are is carbon atoms essentially arranged differently that give rise to different molecules. For example, diamond, as in this question, so is each carbon bonded to 4 other carbons. So if we have a look at this one over here, we've got a carbon and that's bonded to 1, 2, 3, 4 carbons. If I get another one, let's get this one over here. That carbon is also bonded to 4 other carbons. It's not showing all of them though as well because it's quite difficult to draw, but they've shown it as branches here. So 1, 2, 3, 4. This carbon over here, 1, 2, 3, 4, and so on. So each carbon in diamond is bonded to 4 other carbons. So that's diamond. You need to know graphite as well. So graphite is bonded to 3 other carbons. So each carbon is bonded to 3 other carbons. So what that gives rise to is a free electron, or we could say a delocalized electron. And that's what allows graphite to carry a charge, so an electric charge, whereas diamond cannot conduct electricity because there's no delocalized electrons. You need delocalized electrons or some free ion in order to conduct electricity. That's why diamond can't. That's why it's a good thing to use diamond for jewelry, because it doesn't conduct electricity. Another thing as well with this being bonded to 4 other carbons, it makes the substance really hard. again, which makes it good for jewelry, and some really expensive drills as well. They also put diamonds on the edge of that drill as well, to make it a lot harder. Okay, so figure 3 represents structure of graphite. As we've just spoken about, each carbon in graphite is bonded to 3 other carbons. So if we look at this, here, there's a carbon, 1, 2, 3 bonds. Let's look at another carbon, this one here. This is bonded to 1, 2, 3. So each of them are bonded to 3, which gives rise to the hexagonal structure as well, that it's got. And it forms layers as well. So in graphite, it forms layers. Graphene, down here. Graphene is the same thing. So is each carbon is bonded to 3 other carbons, but instead of there being multiple layers, we just take out just the one layer. So graphene is just one layer of that. And what makes that good is, so graphite is quite a strong substance, but if you've got one layer of it, it's quite small, so you can use it in stuff like phones, for example, to conduct electricity because it's really strong, and we could conduct a charge in it because there's one delocalized electron. Okay, so in graphite, each carbon atom forms covalent bonds. Yeah, so allotropes of carbons, these are all covalent bonds, because covalent means non-metal to non-metal. And these are all the giant covalent structures, not the simple ones. Simple covalent structures are stuff like oxygen, water, chlorine, for example. They're all the simple ones. It says how many covalent bonds does each carbon form in graphite? So we've already spoken about that. That's 3. You could just count that off the diagram as well. So graphite conducts electricity. Which particle carries the electrical charge through the graphite? So we've already said it's the electrons, but it's the delocalized electrons. So try and not say free electrons. On the mark scheme, they tend to have written delocalized. Delocalized just means free. So delocalized electrons are what carry the electrical charge through graphite. And just to reiterate, the diamond does not have that. Okay, figure 4 represents the structure of a fullerene. A fullerene, again, is an allotrope of carbon. This is made up of carbon as well. It says where fullerenes used. We use these in electrical components because, again, they can conduct electricity. So that's where we use fullerenes. Describe the structure of the fullerene shown in figure 4. So for 2 marks, we're literally just describing it. So as you can see, it's got a hollow shape going straight through it, right? So we can say it's got a hollow shape. What's another structure that you could see? Well, you can see each of them. They've got that hexagonal ring structure as well. So we can even say that as well. Hexagonal rings of carbon, because it's made up of carbon. You could have also said as well that each carbon atom forms 3 covalent bonds, but we could see that here as well. So there's 1, so 1, 2, 3. So each of them bonding 3. Another one here, 1, 2, 3. So that's where the delocalized electron comes from as well. So yeah, you could have also said that as well. Okay, moving on to question 5. A student investigated the temperature change. So temperature change when different masses of zinc was added to copper sulfate solution. Whenever you get in these questions about experiments, but in biology, chemistry, and physics, you should always in your head think, okay, something along independent variable, dependent variable, and control variable. So just to remind you from yesterday, the independent variable. So independent, we've got dependent, and we've got control. It's not worth learning the full definitions for these. You just need to be able to know how to identify them. So control is what you keep the same. You're controlling it so it doesn't affect your investigation. So for example, the control here would probably be the amount of copper sulfate solution you use. You're changing the zinc here. You're using different masses of zinc. So we don't want the amount of copper sulfate solution you're using to affect this. So we would keep that the same. That's a control. Maybe the cup that you're using as well, keep it the same. Don't start using different cups as well. The area that you're in, so the temperature of the room that you're in, because you're investigating temperature. We don't want to do one experiment like somewhere where it's quite hot and then another where it's quite cold. Okay, so that's your control variables. Your dependent variables is what you're measuring. So measure. And then your independent variable, this is what you're changing. So you can see here, independent, we're changing the masses of zinc, and the dependent, we're measuring the temperature change. Okay, so this is the method that they used. We'll come back to this, but I can see what they're doing anyway. They're pouring the copper sulfate solution into the cup. They're measuring the starting temperature. They're adding 1 gram of zinc, so with the spoon there. They stir the mixture and they're measuring the highest temperature that's recorded. And then they repeat the steps, but they use different masses of zinc each time because that's what they're investigating. So the student varied the mass of zinc. What type of variable is the mass of zinc? So they're changing the mass of zinc, so it would be the independent variable. Because that's what they're changing. If they ask the dependent variable here, this is the temperature change because that's what they're measuring. And control, there's quite a lot of control variables that they would use here. Okay. Zinc reacts with copper sulfate solution to produce salt A and copper. The word equation for the reaction is so-and-so. What's the name of salt A? Now remember, whatever's on your reactants has to come out of the products. And if we look at the product, so we've got copper there, which is here. So then the salt must be whatever's left behind. So the zinc sulfate has to be salt A in that case. Zinc sulfate. So that's how you work it out. Okay, another thing that's worth mentioning here as well, they could also ask you the word equation as well. So the sulfate ion, remember, is SO4 2 minus. You have to remember that. There are certain ions that you need to remember, and sulfate 2 minus is quite a common one to know. Okay, the temperature of the solution increases when zinc reacts with the copper sulfate solution. Give 2 other observations that could be made when zinc reacts with copper sulfate solution. So this would be the color changes. So you would say the solution becomes colorless when the zinc reacts with the copper sulfate solution. So the solution becomes colorless. And then you would say that a solid is produced as well. Solid produced. Okay, so solution becomes colorless and a solid is produced. You have to remember them 2 things when a metal reacts with a metal sulfate solution. Okay, question 6. So we've got a 250 centimeters cubed solution of copper sulfate containing 6.52 grams of dissolved solid. So the solution containing this much dissolved solid. It says calculate the concentration of the copper in grams per decimeter cubed. So first things first, there's an issue with this here. The solution's in centimeters cubed, but my final answer is going to be in decimeters cubed. So I need to change that 250 centimeters cubed to decimeters cubed first before plugging it into this concentration equation. In case I don't give you this concentration equation, you can kind of figure out what you're doing by looking at the units. So you can see it's grams per decimeter cubed. That minus sign is essentially divide. So it's grams over decimeter cubed like that. So we're doing mass divided by volume. So that's how you work it out from the unit. So we can see here it's mass divided by volume. Just in case they don't give you it, just look at the units. You can figure out what the equation is by that. Okay, so we need to change that 250 to decimeters cubed. So and then we need to divide them. So we've got concentration equals the mass, which is 6.52. We're dividing that by 250 centimeters cubed, but then we need to times by the 1,000 to account for the change in units for this to decimeters cubed. Putting that in the calculator. Divided by 6.52 divided by 250, and then we times that by 1,000, we get 26.08. So that's my answer. Just to show you another way to do it, because some people prefer changing the units beforehand as well. So 250 centimeters cubed. To change that to decimeters cubed, just divide by 1,000. So if I do 250 centimeters cubed divided by 1,000, I get 0.25. And then you could substitute that into the concentration equation. So 6.52 divided by 0.25, you'll get the same answer. 26.08. Let me just double check you get the same answer. 0.25. And yep, you get the same answer. So it's up to you which method you want to use. You could use method 1, or you could use method 2. So in method 1, I just plugged everything in, but then had to times by 1,000 to account for the change in units. However, if you want to change it to decimeters cubed beforehand and then plug it into the concentration formula, you can also do that as well. Okay, moving on. Part B, sodium hydroxide solution and copper sulfate solution were reacted together completely. So meaning all the reactants had completely reacted to form the product. The result was a mixture of a precipitate, remember a precipitate is just a solid, of copper hydroxide in a solution of sodium sulfate. Describe how to obtain a pure sample of solid copper hydroxide from the mixture and a pure sample of solid sodium sulfate from the mixture. Okay, let's start off with the copper hydroxide. So it's 4 marks because 2 marks for each of them. So starting off with the copper, solid copper hydroxide. Solid copper hydroxide. Okay. So what you could say with this is we are going to filter off the copper hydroxide and then dry it essentially. So filter the copper hydroxide. The reason why we're filtering it is because we want a pure sample. So we filter it, and then once we filter it, we dry the solid because we don't want, we would just want it solid at the end. So we're going to dry the solid because it is a solution. For both of them are solutions. When they then react, you want to get that solution out for it to become solid. Okay, so that's your 2 marks for the solid copper hydroxide. Now the solid sodium sulfate. So with this one, you're gonna pour it into the evaporating basin and you're gonna heat it. So pour. So we're describing crystallization basically. So pour solution into evaporating basin because we're going to heat it. We're then going to heat it to evaporate water from solution. And then once you've done that is the crystallization process. So you're crystallizing it. So once you've heated it, you've taken all the water out, you're then going to dry it so it crystallizes. So a bit similar to the one above. Okay, and that's your 2 marks. So just dry the solid. You're drying them both because they end up both being solids at the end. Okay, let me just double check I've not missed anything. So precipitate of copper hydroxide in a solution of sodium sulfate. Okay, so just to reiterate why I know that's that way as well. So a lot of students get confused. Well, how do you know that the sodium sulfate, the way I've done the crystallization process, isn't the copper hydroxide? If you look at the question, it says the result was a precipitate of copper hydroxide. So the copper hydroxide is already a solid. So because it's already a solid, I just need to filter out that solid because it's already a solid. And then you just need to dry it. Whereas the sodium sulfate is a solution. So because that's a solution, I need to heat that solution and get out the solid because at the end, they want both solids. So that's how you know when to do crystallization and when to just filter it. Filter it if it's already a solid. Crystallization if it's a liquid or solution and you want to turn it into a solid. Okay, and that's 4 marks. Okay, part C, we've got something to do with electrolysis there. Figure 6 shows the equipment used to electrolyze a sample of sodium sulfate solution. So we've got the solution there. We've got 2 electrodes. The electrodes are made up of graphite. We've got the positive and negative. charges coming from the supply. So it says graphite electrodes are used in electrolysis. Give 2 reasons why graphite is a suitable material for the electrodes. So you could say that it's inert. What inert basically means is that it won't react with anything that's within the solution. Let me just try that again. So the word inert. Another place where you'll hear about the word inert is everything that's in group 0 or group 8, the noble gases, they're all inert gases as well because they've got full outer shells, so they don't react with anything as well. That's what inert means. Another reason why they use graphite is because it conducts electricity. As we spoke about before, it's got one delocalized electron, and you need the electrodes to be able to carry an electrical charge, so graphite can conduct electricity. That's why we use it. Okay, sodium sulfate solution contains ions. Ions are just positive or negative ions. Which ions are attracted to the positive electrode during electrolysis? Now, the ones that are going to the positive electrode are the negative ions. So think about physics. Positive and positive and negative, these repel each other. If you've got the opposite charges, these attract. So the ones that are going to attract with the positive electrode are going to be the negative ions. Now, which negative ions are they going to be? Well, we've got sodium sulfate solution. So in the sodium sulfate solution, we've got sodium plus. And the reason why I know it's plus is because it's in group 1, so it loses 1 electron. The sulfate ions are SO4 2 minus, so it's a minus charge. So SO4 2 minus will be attracting to that. So I can see the only option here with SO4 2 minus is this one here. But it's also got that OH minus. So where's OH minus coming from? The OH minus is coming from the solution that it's in, so the water. So remember, the water splits up to H plus and OH minus. So the two negative ions are attracted to the positive electrode is OH minus from the solution that it's in, and the SO2 4 minus from the sulfate solution as well. Okay, so that's SM2. Draw one straight line from each electrode to the product formed at that electrode during electrolysis of sodium sulfate solution. So the cathode attracts cations, and cations are positive. So the cathode is negative, and the anode is positive. So you can remember it using this. So the panic mnemonic, I'll leave it there actually. No space. There. Okay, so the panic mnemonic stands for positive anode, negative is cathode. So you can remember it that way as well. So we can see negative cathode, positive anode. Where people get confused as well is the cations, which attract to the cathode, are positive because positive attracts to negative. So let me just write that here as well. So cations are positive. So you can remember if you like cats, and that's positive. And positive has to attract to the negative cathode. So the cations attract to the cathode. And then the anions, they're going to attract to the positive anode. So something to attract to positive is going to be negative. So try and find your own means of remembering that, but it is worth probably using the panic mnemonic. You know what charges the electrodes are going to be, so therefore the ions of them are going to be the opposite, because opposites attract. Okay, so we need to know what's going to go to the positive anode and the negative cathode. So the negative cathode, the positive ions are going to go there, and the positive one here is hydrogen, because H plus changes. H plus is a positive cation, which then changes to hydrogen. The anode is going to have anions, which are negative. The oxygen, which has 2 minus, that would go there. Draw one straight line from each electrode to the product formed at the electrode during the electrolysis. Yeah, so hydrogen and oxygen form. Okay, so let's move on. Electrolysis is one that quite a lot of people are not a fan of, but there's quite a few different electrolysis examples that you need to know. So if you look on the summary sheet, there's like electrolysis of a solution, there's electrolysis of when you're separating out metals. You need to know all the different case scenarios. That was a solution one, and they're all slightly different as well. So definitely do have a look at that as well. Sodium carbonate has the formula Na2CO3. In case they don't tell you that, I'll tell you how you figure that out. So sodium has a one plus charge because it's in group 1. It loses 1 electron, so it becomes 1 plus. Carbonate is again something that you need to remember is 2 minus. You have to remember that, just like sulfate's 2 minus. And then what you do is you just cross them both over. So you've got sodium and then you've got carbonate. That 2, let me just choose a different color. That 2 is going to drop here. The 1 is going to drop there, and the 1 doesn't really affect it. So that's where sodium 2 carbonate comes from, like that. So carbonate is something that you do need to memorize as well. Oh, it's already told us here as well. I didn't spot that. The atomic number of sodium is 11. What's the electronic configuration of the sodium ion? So the sodium ion has lost 1 electron. So this 11 becomes 10. And if I was to list out 10, you have 2 in the first shell. You can have up to 8 in the next shell, and 2 plus 8 gives you 10. So it would just be that one, 2, 8. Okay. For 3 marks, it says explain why solid sodium carbonate cannot conduct electricity, but a solution of sodium carbonate can conduct electricity. Now remember, for something to be able to conduct electricity, either it needs free electrons, delocalized electrons, or it needs free ions to move around. And if solid sodium carbonate, the ions are not free to move around in solid. However, if you make this solid, there's 2 things you could do. You could make it molten, or you could put it in solution. And doing one of these 2 will basically allow the ions to move freely. And if the ions can move freely, then it can conduct a charge. So that's what we're saying. So you would say in a solid, the ions are essentially held by strong electrostatic forces. So remember, with ionic bonding, you're always speaking about electrostatic forces between the positive and negative ions. So in a solid, the ions held together by strong electrostatic forces. Remember, you cannot speak about electrostatic forces in covalent bonding because you only speak about electrostatic forces between something positive and negative. There's no positive and negative within covalent bonding, just ionic. So the ions are held together by strong electrostatic forces. So the ions cannot move because of that. The second mark, you explain that. So the ions cannot move. And if they can't move, they can't conduct electricity. Whereas if you put it in a solution, the ions are therefore free to move. So in solution, the ions are free to move, so can conduct electricity. So even if you get 1 in terms of molten as well, you might have to give a reason as well. Molten would be the exact same thing as well. So molten and in solution with ionic compound. So this is an ionic compound because you've got sodium carbonate. It's the same reason. So that's where your 3 marks comes from. Okay, part B. Calculate the percentage by mass of sodium in sodium carbonate. So we want to work out what's the percentage of sodium in this whole thing here. They've given you the equation. So total relative atomic mass of the element. So for sodium, that's just 23. But there's 2 of them, so be careful of that. There's 2 times 23. And then the relative formula mass of the compound. So we've got 2 times 23 for the sodium, plus for the carbon, we've got 12. I'm just reading them from here, by the way. If you don't get given them, you have to get them from the periodic table, the mass numbers. And then we're adding oxygen, 3 of them, so 3 times 16. And we times our answer by 100. So if I put that in the calculator, what do we get? 2 times 23 over Add 12. Okay, so we get 43 point, we get quite a long number. I'll just give it to one decimal place because it doesn't tell me how much decimal places to give it to you or significant figures. So I'm just going to say 43.4%. Yeah, they've not said how much decimal places or significant figures. So just to reiterate, it's the total relative atomic mass of what you're trying to find. So in this case, it was a sodium. We want to know how much sodium is there in all of that. So 43% sounds like a good good answer for that. If you ended up getting something over 100%, you've definitely gone wrong as well. You can't have a number bigger than 100%. Okay, question 8. Mixtures can be separated by different methods. Figure 7 shows apparatus used to separate the dyes in the black ink. This is chromatography. As soon as you see that paper, the line drawn on it and some water traveling up it, that's chromatography. So what's the name of this method? You could say paper chromatography, but even if you said chromatography, you'd get the answer. So chromatography. So some water was added to a mixture of two solids, C and D. The mixture was stirred and then poured into the apparatus shown in figure 8. So we've got the solid C, it's in a funnel, and then I guess it's passing through the filter paper down into the beaker where the solution of D is. Name the separation method shown in figure 8. So it's just filtration. Explain why solid C separated from the mixture. Explain why solid C separated from the mixture of C and D. Explain why solid C separated from the mixture of C and D. I guess because it's insoluble, right? So the reason why it stayed behind was because it can't dissolve in that solution of D. So you would say solid C is insoluble, meaning it cannot dissolve in D. So because it's insoluble, it stayed on top, whereas the solution D, let me get rid of this, I'll just write C. Whereas D is soluble because it dissolved in and it passed through. So we're just speaking about solubility there. So insoluble means it does not dissolve in water. I'll just write that down. So so does not dissolve in water, whereas soluble does dissolve in water. So when you're speaking about filtration, it's all about solubilities. Okay, moving on. A student separated a mixture of 3 liquids, G, H, and I. Okay, so G, H, and I is all in there. You should recognize this as distillation. They've added heat, and then that's going to change the liquid to a vapor, as it says there. So it changes to a gas. That then rises and comes down this part, which is called a condenser. And this condenser is really cold. So what happens is that gas changes back to a liquid because it's cooled down. And when it's changed back to a liquid, it's going to drop into this conical flask. Okay, so we name the separation method shown in figure 9. This is distillation. And it's the same method that we use in fractional distillation as well. But what fractional distillation is, when you're separating out crude oil, you should recognize it as the really big thing where it's got separate taps, is there's loads of different sized hydrocarbons in crude oil. So there's so many different taps where they come off on. I think I've got a question on it anyway, but same thing, but on a bigger scale, more fractions. Okay, question 9. Magnesium chloride is a soluble salt, meaning it dissolves. Magnesium reacts with hydrochloric acid to produce magnesium chloride and a gas. Which gas is produced? Well, if you've got magnesium reacting with hydrochloric acid, so you've got magnesium, hydrochloric acid, and if magnesium chloride is produced, so we've got magnesium there, we've got, I'm not going to deal with the atoms right now, I just want to know what's in each. So we've got the magnesium, we've got the chlorine, which is here, so what's left behind is just that hydrogen. Now, hydrogen cannot be like just H by itself like that. So if you are writing it as a chemical formula, remember hydrogen is diatomic, so H2. Remember the side effect of hydrogen as well is that it's flammable, in case I asked that as well. So I'm just going to write hydrogen like so. But remember, it's diatomic. So if you do write the elemental version of it, it's H2. Magnesium chloride can be electrolyzed when molten. So similar to what we said before, this is an ionic substance, magnesium chloride. Magnesium is a metal, chlorine is a non-metal. If it was in solution, it can conduct electricity. But it can also conduct electricity when it's molten as well, because the ions are free to move. So it's quite good to see both them examples. Which represents molten magnesium chloride. So magnesium is in group 2. Well, all of them are the same actually. Magnesium chloride. I'll explain how they got MgCl2. So magnesium's in group 2, so 2 plus. Chlorine's in group 7, so 1 minus, because it only gains 1 electron. So then if we cross them over, the 2 is going to drop to there. The 1 drops to here. I don't really need that 1 there, so it's just MgCl2. So that's where they get it from. Now, because it's molten, it's not solid, because that wouldn't be able to conduct electricity. It's not a gas. Molten, think about like lava, so it's liquid. So we're looking at the state symbols. Remember, you could also have aqueous as well, which just means it's dissolved in water solution. Okay. Magnesium chloride contains Mg2 plus and Cl minus ions, which we've just said over here. Name the product at each electrode when molten magnesium chloride is electrolyzed. So the negative electrode is going to attract the positive ions. And the product at each electrode, when it's electrolyzed, then removes that ion. So the magnesium 2 plus at the negative electrode just becomes magnesium. A really common mistake that students make is they write Mg2 plus. It's saying name the product at each electrode when it's electrolyzed. So it loses that ion and it just becomes its normal element that it's meant to be. At the positive electrode, you're going to have the Cl minus ions, and then Cl minus ions just turn into chlorine. Now, again, just want to reiterate, if you are going to end up writing the elements to these, magnesium, you're fine to write as magnesium like this. But with chlorine, if you wrote Cl, you would have lost the marks, because chlorine is a diatomic molecule as well. It exists as Cl2. So if you're going to write it as elements, it's Cl2. That's why it's better to just stay safe and just write the words if you can. Okay, next question. When heated, 0.72 grams of magnesium reacts with iron oxide to produce 2.32 grams of products. Calculate the mass of iron oxide that reacts with 0.72 grams of magnesium. Now, what this is testing you on is that conservation of mass. Now, what conservation of mass is that whatever reactants you put into a reaction, you're going to produce the same amount of products. So the mass has to be the same. You can't have a decrease or an increase in mass. It's a bit like conservation of energy. Energy is just never created or destroyed. It's just transferred. It's never lost. So sometimes the products might be less in weight, though, when you do a reaction. That's because it's dissipated as a gas. So just keep that in mind. So here, if we're heating 0.72 grams of magnesium with iron oxide, which I don't know how much iron oxide that is, and that's going to produce 2.32 grams of products. So these are my reactants, and this is my products. And they've just said work out the mass of iron oxide, so this missing number here. So I need both the left-hand side and the right-hand side to be the same. So to work out that missing number here, all I need to do is just minus 0.72 to the other side. So I'm doing 2.32 minus 0.72, which gives me 2.32 minus 0.72. That gives me 1.6. Just check your answer as well. 0.72 add 1.6 gives you 2.32 as well. So 1.6 grams. So that's just testing you on conservation of mass. The student used 30 centimeters cubed of magnesium chloride solution, 1 decimeter cubed of magnesium chloride solution. So notice a change in units here. Contains 180 grams of magnesium chloride, and they've told us 1 decimeter cubed is 1,000 centimeters cubed. But they will always tell you that, just like that last question we did, they expected you to know to change the centimeters cubed to decimeters cubed, you had to divide by 1,000. So the flip way for centimeters cubed, decimeter cubed is your times. They're not always going to tell you though. It says calculate the mass of magnesium chloride in 30 centimeters cubed of magnesium chloride solution. So if we know in 1 decimeter cubed, of magnesium chloride solution, so I'm just going to write in solution, we've got 180 grams of magnesium chloride. Okay, so in 1 decimeter cubed of magnesium chloride solution, we've got this much magnesium chloride inside it. I've just rewrote this part of the question. Now, if I want to analyze it in terms of centimeters cubed, I need to change this 1 decimeter cubed to centimeters cubed, and they've told me 1 decimeter cubed is 1,000 centimeters cubed. So I'm just going to say 1,000 centimeters cubed is 180 grams. I'm not going to write that down again, just to save time. So 1,000 centimeters cubed is 180 grams of magnesium chloride solution. I want to know how much in 30 centimeters cubed. So this is all proportions. You'll notice how in chemistry, there's a lot of your GCSE math skills that they're testing you on. So how do I get that 1,000 down to 30? What I could do is I could change it to 10. So to get this down to 10 centimeters cubed, I'm going to divide by 100. I'm going to divide this side by 100. So I end up getting 1.8 grams. Now to get that 10 centimeters cubed to 30 centimeters cubed, as it asked for in the question, I'm just going to times by 3. Whatever I do to one side, I do to the other side. So times by 3. 1.8 times 3 gives me 5.4 grams. And that's my answer. So it was all about proportions. We converted units again. They were quite nice to give us this. They don't always have to give it though. As you saw in the last question, they did not give that. So make sure you know your conversions between centimeters cubed and decimeters cubed. Okay, question 10. Figure 12 represents the structures of pure copper and an alloy of copper and zinc. Now, an alloy just means mixture of metals, whereas pure substances just have one metal inside. So you can see pure copper there, and you've got an alloy of copper and zinc. Alloys are the more common ones around the world that we use because they're a lot more harder. Explain why the alloy of copper and zinc is harder than pure copper. That's like a classic question that they always ask with alloys. All we're doing is we're just describing both these diagrams. So in essence, just before I write this down, you can see with the pure copper, all the atoms are the same size. So because they're all the same size, they all slide over each other. So when they slide over each other, that's what makes it malleable. It's quite a soft metal. Whereas if you start mixing metals together, you can see it's starting to distort it. So these are not able to slide along each other anymore because they're not the same size. So that's what it's about. So how can we write that idea down for 3 marks? So you're going to say the alloy is harder. So the alloy is harder because the atoms are different sizes. So it's got multiple atoms of different sizes. It's quite nice that they've drawn the diagram there, but again, they don't have to draw the diagram. Okay, so that's your first mark. You've identified that in an alloy, the atoms are all different sizes. So because the atoms are all different sizes, you just distorted the layers. The layers no longer can slide over each other. So you would say the layers are distorted in that alloy. So what does that mean? The layers cannot slide over each other. Cannot slide over each other. And that's your 3 marks. You could have said it the converse way as well. You could have talked about pure copper all being the same and they slide over each other, and if you want to do comparison that way as well. But that's your 3 marks. That's there. Okay, we've got another calculation question. 5.25 gram sample of an alloy of copper and zinc contain 13.5% zinc by mass. Okay, so just thinking about that statement, if you got 5.25 gram of an alloy of copper and zinc, so it's only got just copper and zinc inside it. If it's got 13.5% of zinc by mass, then I know to work out how much copper there is as a percentage, I just need to do 100% minus 13.5%, which gives me, just work that out. Always try and understand the question as you're reading it. So that's 86.5%. Okay, so I know copper, there's 86.5% of copper within that alloy. Calculate the mass of copper in that 5.25 grams sample. Now that I know that there's 86.5%, so that's my first mark by working out that calculation. Let me just put that down here. So I've worked out how much copper there is by minusing the percentage, so 100% minus 13.5%. Now all I need to do is that 86.5%, I need to just work it off the 5.25 grams sample. To put that in your calculator, change that percentage to a decimal, so you divide it by 100, so you get 0.865. Of just means you times by 5.25. Again, your GCSE math skills. Putting that in the calculator, 0.865 times 5.25. Okay, so I've got a long number. It says give it to 3 significant figures. I'm just going to write the full number that's here. 5.54125 grams. Giving that to 3 significant figures. The third significant figure is this one here. The 1 keeps that 4 the same. So my answer is just 4.54 grams. And that's my answer. Just check that. Yep, that's right. Okay, so that's quite a nice 4 marker that they're giving just for using your GCSE math skills in chemistry. And a lot of chemistry is that, a lot of physics is also that as well, which you'll see in tomorrow's class as well. Okay, question 11. A student prepared copper sulfate by reacting an acid with excess copper carbonate. Now, whenever something's reacted in excess, it's basically because they want the reaction to fully be completed. So if they've got copper sulfate and they're reacting it with an excess, they're reacting the acid with excess copper carbonate, is because they want the acid to fully react. That's the reason why they're doing it. Okay, so it says figure 13 shows the first 2 stages in the preparation of copper sulfate. So we've got stage 1. They've got copper carbonate, they've got a beaker and acid, they're putting the copper carbonate inside. And then stage 2, they get their solution and they're filtering it. So they're putting it through filter paper. Okay. Saying what's the formula of the acid used to prepare copper sulfate? Now, if the copper carbonate is changing to copper sulfate, we need an acid that has that sulfate in, and we can see the sulfate ions here. So it's sulfuric acid. Make sure you know the names of these. So that's sulfuric acid. This is nitric acid. So we call this the nitrate ion, and then that's your hydrochloric acid. Hydrochloric acid. So they're the 3 common acids they use. Okay, so the question says, why is excess copper carbonate used in stage 1? It's so all this acid reacts. So all the acid reacts. So that habit of answering questions before you've actually looked at the questions is a really good habit as well with answering these papers, because you fully understood what they're telling you, and then you're just writing the answers down. Okay, beaker N contained copper sulfate solution. Where's beaker N? There's beaker N. Contained copper sulfate solution. Describe how the student could produce copper sulfate crystals from the copper sulfate solution in beaker N. So again, this is the crystallization question. Whenever you've got a solution and you want to form crystals, you're just describing crystallization, but you can't just write the word crystallization. You need to describe how you actually carry it out. So with crystallization, you heat the solution. So similar to the question, well, exactly the same as the question we answered above. So you're heating the solution. The reason why we're heating the solution is because you want to remove some of that water from the solution. And then once you've done that, is you're leaving it to cool. So it, not cool. So it crystallizes. Okay, that's 2 marks. Okay, question 12. Table 8 shows a diagram which represents the structure of 2 substances. So we've got sodium chloride, which is an ionic substance. It's ionic because it's a metal and a non-metal. And then we've got oxygen, which is a covalent structure because it's non-metals. Oxygens are non-metals, so it's covalent. Okay, so I've identified that. I can see the positive and negative ions here as a lattice structure over here. And I can just see there's 2 oxygens there with 2 bonds. Compare the structure and bonding of sodium chloride and oxygen for 6 marks. There's a brilliant 6 marker. It's just testing you on bonding. So we're comparing them. If we're comparing, we're basically giving what's the similarities and the differences. I guess most of it is going to be differences, but if I was to say in terms of similarities, I would say both their bonds are strong. Ionic bonds and covalent bonds are strong. And also, whenever you've got bonds in terms of ionic and covalent, you've got full outer shells. So that's the similarities between both of them. I'd say that's the hard part to identify because it's easy to spot the differences. But comparing similarities and differences. So similarities both have strong bonds. Even though they're different bonds, they're still strong. Ionic bonds are strong. Covalent bonds are also strong. And they also both have full outer shells. That's the reason why they've bonded together in this manner. So they get the full outer shells. That's what it's trying to achieve. Okay, so they're the only similarities. Now let's talk about the differences between each of them. So you would say sodium chloride, NaCl, is ionic. And oxygen is covalent. And you can speak about each of them as well. So you could say, oh yeah, another thing you could actually say as well, differences. This is made up of, I'm going to write up here. This is made up of two elements, sodium and chloride. This is just made up of one element, just oxygen. Even though there's two of them, it's still just only oxygen. So that's another difference as well. So we've just said ionic, covalent. You could say two elements and one element. You could say the difference is the oxygen is non-metals, whereas sodium chloride is metal and non-metal. That's also a difference as well. You could say sodium chloride, this is a giant structure of ions, whereas oxygen is just a small molecule, or simple molecule, you could say. Simple, small molecule. You could say this is an ionic lattice structure. That's also a difference as well. You could speak about how there's no charges in the oxygen. There's no charges here, whereas there's charges here. So there's positive metal ions, or positive sodium ions, or negative chloride ions in that first one. You can speak about that as well. Just trying to see if I've missed anything. That's it really. You're just describing the differences between ionic and covalent. So yeah, that's quite a good 6 marker that's there. Okay, question 13. So in one reaction, the temperature of a reaction mixture decreases. Which word describes this type of reaction? Now, again, this is where people get confused as well. So it's going to be, we're talking about exothermic and endothermic reactions here. Now, when we're talking about reactions, let's say this is the system and this is the surroundings. This is how you should be thinking about it. Your system is where the reaction is actually happening, the exothermic or endothermic reaction, and then you've got the surroundings around. Now, if this system is giving out heat, that's so if it's giving out heat, that's an exothermic reaction because heat is leaving. However, if the temperature hold on, use a different analogy. So an exothermic reaction, I'll give examples so you can envision this. So exothermic reactions are the more common reactions. So stuff like combustion. So endothermic. Okay. So exothermic reactions are the ones that give out heat. So stuff like combustion, stuff like respiration. That's also an exothermic reaction. These are the more common reactions that happens in the world. Endothermic reaction, a good one of that is photosynthesis. So it's taking in heat, the light energy for photosynthesis to take place, right? So let's see what this question is saying. It says in one reaction, the temperature of a reaction mixture decreases. Which word describes this type of reaction? So it's not displacement. Displacement is a reaction where you display a reactive metal or any reactive substance, usually the metal, displaces a less reactive one. So displacement, move it out of place. It's not neutralization, because neutralization is where you've got an acid, base or alkali. I'll just say alkali, and you get salt and water. So that's your neutralization reaction. So if the temperature of the reaction mixture decreases, that's going to be an endothermic reaction. Okay. So in an experiment, salt is dissolved in water. Okay, so the temperature change is measured. So I can see there's a polystyrene. I'm guessing it's polystyrene cup. Whenever we're using temperature changes, that's what tends to happen. But it's also held within a beaker. Figure 3 shows the apparatus that was used, and it's got a thermometer as well. State what is used to measure the temperature change. Well, it's just the thermometer. So it's just a thermometer that's measuring the temperature change. State one reason for using this piece of equipment in figure 3. So equipment A is just a beaker. Why would you use a beaker? You would want to stop the polystyrene cup from falling, I guess. So you could just say stops polystyrene cup from falling over. That's why they put the cup inside the beaker. A student suggests putting a lid on the piece of equipment B. State why this would help give a more accurate value for the temperature change. Well, if you put a lid on top of equipment B, no heat is escaping. So you could just say reduces heat from being lost to surroundings. Okay, moving on. One of the salts dissolved in barium chloride. One of the salts dissolved is barium chloride. Okay, so that's a salt. Barium chloride contains a chloride ion Cl minus. Give the formula of the barium ion in barium chloride. So it's kind of like working backwards. So you've got barium, you've got chloride, which is Cl minus. And if you cross it over, so barium chloride, the one has dropped here, and we could see there's a 2 here, so we're just working backwards. So that must mean that this must be 2 plus, so it's barium 2 plus. So that's how you work it out. If you look at the periodic table as well, barium, where's barium? Barium is in group 2, it's here, so it is a 2 plus ion anyway, if you just wanted to work it out from the periodic table, rather than working out that way. Okay, let's go back to here. Okay, just going to go quite fast through the last few, just because of the time. Figure 5 shows a structure of one molecule of 3 different compounds. We've got X, Y, and Z. They're all hydrocarbons because it only contains just hydrogen and carbon. The molecules of the compounds shown in figure 5 all contain the same number of carbon atoms, which you can see all of them have 3. Give the number of carbon atoms in a molecule of compound X. Well, there's just 3. 1, 2, 3. You're just counting it. Compound X contains carbon and one other element. Give the name of the other element in compound X. They're just hydrogens atoms. Which of the compounds in figure 5 is a hydrocarbon? All of them are hydrocarbons because they all just contain hydrogen and carbon. So all of them are, so X, Y, and Z. Just cross that one. Which of the compounds in figure 5 have the same molecular formula? So how much carbons and hydrogens do each of them have? So this has 3 carbons and 1, 2, 3, 4, 5, 6 hydrogens. This has 3 carbons and 1, 2, 3, 4, 5, 6, 7, 8. This has 3 carbons and 1, 2, 3, 4, 5, 6. So it's X and Z that are the same. So it's just X and Z that have the same. So it's just that one. So because it's got the same amount of carbons and hydrogens. Figure 6 shows where fractions are produced in fractional distillation of crude oil. So we spoke about simple distillation before. This is fractional, same thing, but it's happily got a bigger scale. They put the crude oil in. There's heat coming from the bottom here. So the ones with the higher boiling point will be on the bottom. And then the smaller ones tend to be on they rise to the top and get sectioned off. The fraction with the smallest molecule is called gases. So it's these ones here. The smallest ones are right on the top. Compared to petrol, the boiling point of kerosene, which is below, is higher. So the ones towards the bottom, these are the higher boiling points. And these are the lower boiling points. So that's how the spectrum works across the fractional distillation one. When petrol burns, one product is, so when you're thinking of combustion, carbon dioxide. So carbon dioxide. You could even say carbon monoxide as well. That's incomplete combustion, but complete combustion is carbon dioxide. You could have even said water as well. So I'll just write the combustion reaction here. So combustion reaction is where you get fuel, you react it with oxygen, and then carbon dioxide and H2O. It are the products. That's complete combustion. If it was incomplete combustion, this carbon dioxide instead becomes carbon monoxide, which is dangerous to breathe in, which is why we have carbon monoxide alarms. So detect that because we can't smell or see it. Okay, question 15. This question's about bromine. Give the color and physical state of bromine at room temperature. This is something that you just need to remember, unfortunately, for all the group 7 elements. So for bromine, it's red brown, the color, and the physical state of it is liquid at room temperature. Bromine reacts with hydrogen to form hydrogen bromide. Write a word equation. We're just writing what's given in the question. So bromine reacts with hydrogen to give hydrogen bromide. Hydrogen. Nice and simple, 2 marker, just literally writing that down. Hydrogen bromide dissolves in water to form a solution. The solution of hydrogen bromide reacts with alkalis. Say the type of reaction that occurs when a solution of hydrogen bromide reacts with an alkali. That's a neutralization reaction that we spoke about before, where a salt and water will form, so neutralization. Bromine and other halogens react with hot iron wool. Figure 7 shows the relative speed of some of these reactions. So we can see fluorine is not populated, chlorine quite quickly, bromine quickly, and then iodine slow, so it reacts down. So fluorine also reacts with hot iron wool. Use figure 7 to predict the relative speed of this reaction. Well, you can see the trend. The higher up it is, the more it will react. So if chlorine is reacting very quickly, then fluorine has to be like extremely quickly, like the fastest out of all of them. So you could say fluorine reacts the fastest. That's why they left the gap there. They try and see if you can spot the trend. You should know as well, as you go down group 7, the reactivity decreases. So you should just know that anyway, even if they didn't give you that table. Okay, we've got another calculation. 1 potassium bromide contains 32.8% potassium by mass. Calculate the mass of potassium and the mass of bromine in 500 grams, same as the other question. So 32.8% of 500 grams. This is going to give me it for potassium. I'll just write K here for potassium because it says 32.8% of that. So to put that in your calculator, 0.328 times 500. 328 times 500, which gives you 164 grams. That's for potassium. Now, we know there's 500 grams altogether, so to work out how much for bromine, just do 500 grams minus 164 grams, and you get 336 grams. And that's your answer. Okay, moving on. This question's about the atmosphere. Describe a test to show that gas is oxygen. So you need to know the gas test for hydrogen, oxygen, carbon dioxide. I forgot what the last one was. Did I say hydrogen? Yeah, so you need to know the test. So for the gas, to show that a gas is oxygen, you're going to add a glowing splint. That's your first mark. And then your second mark is what's the test if it's a positive test. So if there is oxygen, then it relights if there is oxygen. If oxygen present. Okay, so that's the oxygen test. Copper reacts with oxygen to form copper oxide. 2.1 grams of copper will react completely with 0.529 of oxygen. In an experiment, this much copper is heated with this much oxygen until the reaction is complete. Calculate the mass of the oxygen remaining at the end of the experiment. So, as you can see, I'm just wary of time and there's quite a few questions. We'll still do it anyway. Okay, so 2.1 grams of copper will react completely with 0.52 grams of oxygen. Calculate the mass of oxygen remaining at the end of the experiment. So we're doing it in terms of percentages. So the oxygen 0.529 We're going to times that by the copper amount that we've got, which is 4.2 out of 2.1 from the one above. So we get 1.058. And then with that number, we're going to minus it from the 50 grams of oxygen. So 50 grams minus 1.058 grams, you end up getting 48.942. It doesn't tell you how much to round this to, so I'll probably just leave all of it that you end up getting. So what we did was we calculated the mass of oxygen, and then we minus that from the amount of copper. Okay, so helium, neon, and argon are all inert. That's because they're all noble gases. Explained in terms of electrons why all these gases are inert is because they've all got full outer shells. So they all have full outer shells. So what that basically means is that they don't need to gain or lose electrons. So they do not need to gain or lose electrons. Okay, so that's your second mark. Okay, we're towards the end. Hopefully we'll get this done in time. Two pieces of steel can be joined by heating the metal pieces with a very hot flame. This process is often carried out in an argon atmosphere rather than air, which property makes argon gas suitable for this use. It's because that it's unreactive. Argon's in the last group, so it's inert. So that's what makes it suitable rather than using air. Okay, I'm just wary of time. Got quite a few to do. So I'm just going to speak through these last few ones. So figure 10 shows how plant life and the atmosphere of the Earth has changed over time. So this stuff you need to know like by memory. So they've given it to you here, but you do need to know this by heart as well. So the atmosphere in early Earth about 3.5 million years ago, about 10,000 years ago, and what it is today. So it's talking about the plant life. You can see the plant life has evolved. So therefore, there would be an increase of oxygen because they're carrying out photosynthesis. And you can see the amount of carbon dioxide in the atmosphere has decreased over time. That's because it's been trapped in oceans over time. So the oceans ended up forming. A lot of the carbon got trapped into there, so it ended up decreasing. And also, if plants came about as well, plants were using that carbon dioxide for photosynthesis, again, decreasing the amount of carbon dioxide. And the amount of oxygen in the atmosphere, you can see it went from none and it has increased. Again, that's because of photosynthesis, that these plants that have evolved ended up photosynthesizing and releasing oxygen into the atmosphere. So for 6 marks, that's essentially what you were explaining about photosynthesis, the changes in the atmosphere, the increase in carbon dioxide as well from here, this point, from 0.03 to 0.04 is because of global warming and the greenhouse effect. So yeah, that's the 6 marks, what we just discussed there. Question 17 says, Earth's atmosphere has changed during the last 4.6 billion years. What is the approximate percentage of nitrogen and oxygen in the Earth's atmosphere? So nitrogen roughly makes up about 80%, and oxygen is roughly around 20%. Nitrogen's unreactive, so that's fine just being there. The approximate percentage of carbon dioxide in Earth's early atmosphere was 95%. Which are the 2 reasons why the percentage of carbon dioxide has decreased since the Earth's early atmosphere? So as I said before, they dissolved in the oceans, which is why it decreased. And another reason why it decreased as well was because plants used it for photosynthesis. So that's the other reason there as well. Carbon dioxide is a greenhouse gas. Which of the following is also a greenhouse gas? Not argon, that's a noble gas. Nitrogen and oxygen, they're already in the atmosphere. So it's methane, CH4. You should know what the chemical formula for methane is. Which of the following is an environmental problem caused by greenhouse gases? It's not acid rain. Acid rain is caused by sulfur dioxide. Global dimming is caused by soot. So soot is essentially carbon molecules that basically be in the air and it starts making Earth like darker. So it's climate change for that one. Okay, last few questions. So figure 1 shows a change in percentage of carbon dioxide in the Earth's atmosphere from 1800 to 2020. Describe the trend for 3 marks. So what you would say is from 1800 to roughly around over here, whatever point that is. Yeah, so you could say just after 1850, it ended up staying the same, so it was constant at this point. And then after 1850, it ended up increasing all the way till after 2000. So that's when the slight increase happened to around 2020, I guess. So yeah, that's how you're describing it for 3 marks. Question 18. Student measured the melting points of 4 substances. Which substance was pure? We can see these all have ranges, these 3. Pure substances, we know the exact melting point, so it's B. And the reason is because it has a specific melting point. Okay, moving on. Okay, final question. So we've got fractional distillation column. It says explain how crude oil is separated into fractions. I'll just explain it just here. So the crude oil is heated, as you can see. So once it's heated, that liquid is changing to a vapor, so a gas. And then what happens is, depending on its boiling point, it will come off into these fractions, depending on what boiling point it is. And as you can see, the temperature is decreasing as it's going up. So as it's going up, the gas is rising, then changes to a liquid, and then gets tapped off at that. So the shorter chain hydrocarbons come off here, and the longer ones down here. Okay, so that's for the 4 marks. The alkane molecule can be cracked to produce smaller molecules. The reason why we crack them is because smaller molecules are more useful for us than the longer ones, so we crack them and make them smaller. It says balance the equation for the reaction. Here's the reactants. There's the products. And remember, conservation of mass, they have to be exactly the same. So if I've got 14 carbons on the left and I've got 8 here, I need how many more? So I've got 14 carbons here. There's 8 there. So to get 14, I need to add 6. So I need 6 small carbons here. So to change that 3 to a 6, I put a 2 in front of there. And that should balance it. You can also check that the hydrogens balance as well, but it should do. Test for alkenes. So it's the bromine water test. So add bromine water, and then the bromine water should change from orange to colorless. So change from orange to colorless if there is an alkene present. Polypropene is made from propene, so poly just means like it's repeating. So what types of substance is polypropene? It's just a polymer, so plastic, but don't say plastic. Polymer is a scientific word for plastic. And then finally, last question. The student investigated the effect of increasing the temperature and rate of reaction. Explain the effect of increasing the temperature and the rate of reaction and refer to particles and collisions on your answer. So when you increase the temperature, so when you increase temperature, you're increasing the rate of reaction. I'm just going to write rate. So you're increasing the rate. And the reason why you're increasing the rate is because the particles have more energy as you increase the heat. So if they've got more energy, they're going to collide more. So this is all about collision theory. Some particles collide more. So essentially, there's a greater probability as well that there's going to be more successful collisions. Catalysts affect the rate of reaction. What is meant by the term catalyst? So a catalyst increases the rate of reaction without getting used up. That's your 2 marks. So that here increases rate but does not get used up. And then finally, what are the catalysts in biological system called? So we did that in yesterday's class. That's just enzymes. And that's it. The last part was quite rushed, so we could get through all of it, but we did manage to get through all of it. I'll get this sent out to you. The recording will also get sent out to you as well, and I will see you in tomorrow's physics class. Thanks for joining, guys.